Let's look at this. Everybody got a white sheet, white set? Okay, these are a warm up here. Consider the two reactions. NF3 going to nitrogen and fluorine. I balanced it for you. One of the few times you'll ever see me balance an equation. Okay? Decomposition reaction. This breaking apart into two molecules. NF3 versus Ni3. Okay? So bond strengths are given. Down below there's a table of bond strengths. We can answer questions about these reactions. Which reaction above gives off the most heat or energy? Which reaction is endothermic? Which reaction is fastest? Are the reactions driven by entropy or not? Okay? You can answer all these. We'll just cancel lecture. Y'all good to go on all that? What should we talk about?
We're out of these.
You're out of the yellow?
Yes.
Not sure why we don't have enough. Maybe the copier ran out of paper and I didn't notice. I'll have to get some more. Okay. Should we talk about these?
Yes, yes.
Okay. Let's look over. We'll eventually get to all that. So let's sort of introduce this here. Line reactions. A line reaction is what I call, and most chemists call, a synthesis. We have reactants, and then a line, and then products. It basically says these react to yield or to provide this. Okay? Your line reaction, sometimes the main organic reactant can be shown on the left, and then your reagents shown on the line. Just another way to show it, same reaction. A lot of times you can show conditions on your line. Okay, temperature and time, or other things. This is just the idea of a line reaction. So if you're asked to show a line reaction for a reaction you're doing, this would be it here. Thermodynamics. Well, you know all this. I'm not going to read it to you. This is all should be reviewed. You can read it on your own. Basically, thermodynamics is summed up by Gibbs free energy equation. Delta G equals what? Delta H. What is delta H? Enthalpy, or your heat. Okay? All right? That's basically your stability. And this is going to come from bond strengths. Bond strengths equate to stability, and stability can ultimately equate to heat. For example, if you burn something, how much heat does it give off? Well, it's based on how strong the bonds are and how stable they are. We sort of mentioned that. T, temperature, what is delta S? Entropy. Which term does temperature magnify? Entropy. You see it magnifying it right there? Multiplying it? Okay, y'all all knew that, right? For some reason I got you knew this. You know the equation, but you don't know the practicalities of it. Okay? So we'll come back to that. So delta H, heat change. Which is better, positive delta H or negative? Okay? Negative. The system losing energy. Okay? The system losing energy is favorable. Exothermic is favorable. Entropy, which is favorable. Positive or negative? Actually, positive. What does positive entropy mean? Positive means that the system's gaining something. What's it gaining? It's gaining disorder. Right? So you know your entropy terms, what positive and negative means, right? Learn all that in Gen Chem. Okay? Now when we do entropy, we will not do calculations. We will just qualitatively assess it, not quantitative. Entropy. Look at this reaction here. This is an alkene reacting with HBr. We did this yesterday. Okay? Carbocation intermediate, bromine acid carbocation, two-step mechanism. By the way, mechanism. I can tell you guys who are really learned the acid-base mechanism versus not, because some of you missed all the acid-base. The acid-base was our first look at an elementary mechanism. Okay? And if you did poorly on the acid-base, you were not thinking mechanistically. You got to think mechanistically. All right? We will move more into mechanisms. If you don't think mechanistically, it's all going to become just, okay? It's analogous to trying to do math and ignoring formulas. Okay? Your formulas are your systematic way of doing your math problem. You don't just memorize all the answers to math, do you? Okay? What's 55 times 55? Quick. You don't know, but you can sit down and do it because you know how to do it. You know how to do mechanisms, you can do anything. That's why you need to learn organic chemistry. Okay? So, look at this. Delta S is negative. That means it's lost disorder. If it's lost disorder, that's like a double negative. What's it gain? Gained order. Why do we say this is gained order? Because two molecules are coming together to make one. So it's becoming more ordered, right? But the system has lost disorder because the system went from two molecules to one. So it was more disordered over here. As it combined, it lost disorder. So delta S is negative. What about the reverse reaction? You know, actually these reactions can be reversed. We're going to be doing this up here. This is test 2. But when we get to test 3, we're going to do the reverse. Okay? What if we reverse it? What if that guy comes backwards? We can show it going this way. What if that one molecule going to 2? Is that more ordered or less? It's less ordered. Let me drop in a vase here and it's shattering into a million pieces. It's like me shattering this into 2 pieces. Okay? It now has more disorder. What is delta S? Positive or negative? Okay, you saw it here, but do you really know it? Okay, you got to make sure the negative and positive and what it means. Okay, you got it all? You may not have it right now, but that's your goal is to know your signs here and this double negative stuff. Okay, what about this guy? This reaction. We take this and we get this oxygen to bond here. Okay, that's more of an organic 2 reaction called a Michael reaction. Okay. Is delta S positive or negative? Well, first let's say order. Is it gaining order or losing order? Looks like one molecule going to 1, so it looks like it's just a wash. But there's something else going on.
Oh, lost the hydrogen bond.
Losing, it lost the pi, right?
Do what?
It lost the pi.
It did lose a pi,
Gained a sigma.
and it made 2 sigma bonds.
Has less,
But that's thermodynamics.
has less freedom to rotate.
We're doing entropy, and the answer is
Has less freedom to rotate.
less freedom to rotate. See, this guy, it's like this, okay? Lots of disorder. So what if I connect my hands? See, now it's less disordered. So this is not as obvious. One going to 2, obviously it's more disordered. But such is another example of where you can get entropy considerations. Okay, ask a question here. In the middle, will this reaction occur spontaneously?
Depends on direction copy, I guess.
1 going to 2. Basically, is that favored, 1 going to 2?
No, but yes.
What does it say up above? What's favored for entropy? Product's gaining disorder. Is this gaining disorder?
Yes.
Yeah, it's becoming 2 molecules. It's favorable. It'll be spontaneous. That's an entropy consideration. Thermodynamically, will this reaction occur? That's a different consideration. Thermodynamics, you're looking at bond strength and stability. Together, those add up to your Gibbs free energy equation. Okay? What we did here is we qualitatively assessed entropy. All right? Now down here we're going to do enthalpy, delta H. This is easier to quantify. Down here we'll actually do calculations. And down here we again have another alkene reaction, reacting with HBr. The HBr adds across the pi bond, and we now have an H and a Br bonded to the two carbons. It's a hydrohalogenation reaction, just like we did yesterday. Carbocation. This is symmetrical though. You can make carbocation on either side because it's the same carbocation. And the Br minus adds to the carbocation. You've got to envision mechanism. Okay, what's the delta H of this reaction? Well, we can actually calculate that from bond strengths. What we're going to look at is what bonds are broken, and let's add up the values. What bonds are formed, add up the values. What's broken when we do this reaction? It's a pi bond. How much is a pi bond worth? Well, this is where we look at the table on the front page. And we see a carbon-carbon. Actually, this table doesn't show that. I got these from some other table.
Yeah, it does.
Does it show carbon-carbon pi bond?
That's H2C, double bonded with eight. CH2 is towards the,
Right here?
yes, there you go.
Okay. Yeah, what it's showing though, it's showing the whole bonding. That's for both the pi and the sigma.
Oh, okay.
Okay,
Do we
yeah.
subtract the sigma out of it?
You might could. Basically, I didn't get these numbers out of the table, okay? If I don't give you a table with the numbers, well, you can't answer the question. Okay? Because you're not going to memorize these tables. Let's do this example. I basically give you these values. I must have got them somewhere else. Okay, a CC pi bond is worth 63 kcal per mole. We'll do another example using the table so you can use the table. What else is broken in this reaction? Are any of the CH bonds broken? No, they're still there. The HBr bond is broken. It's worth 87. Now the HBr is probably in that table, but it might be different. What does it say for HBr?
87.
It does say 87, okay. That's what's broken. We add these up, 150 kcal per mole is broken. What's formed? I see a new CH bond. Everybody agree there's a new CH bond formed? All right, and the carbon is sp3. So how much is that worth? 101. Now I think some of these may vary from that table, because I got them from a different table. Up here in this table, what are they giving? They're giving H's on different types of carbons. They're all sp3, but they have different lengths here. 101, that's an H bonded to what, 2 carbons. Sort of what we got there. All right. And then a CBr with the carbon being sp3. What does it say in the table? Yeah. You see, I got this from a different table. The table I got it from said 69, and the carbon's sp3. Okay. Probably the table I got distinguished carbons between primary, secondary, tertiary. And that carbon there is what type of carbon? Primary, so it's a primary carbon CH bond. That's what was formed. Was any other bonds formed in this reaction? No. Okay. Now you got what's broken, what's formed, what's the difference in the two? 20. Okay. What's the net here? Is it positive 20 or negative 20?
It's negative.
Why you say it's negative?
Because it's energy of the broken bonds minus the energy of the new ones. It's 150 minus 170.
Why you say it's 150 minus 170 minus 150?
Because of the formula.
Where's the formula?
Change in H reaction equals energy of bonds per minus energy of new bonds.
Okay, okay. Well, let me tell you another way to do this. Okay? The way that, so you understand what's going on with, as opposed to just doing it how you're told with. Okay. Which side is more stable?
Do what? Or the right?
When we went from 150 to 170, are the bonds now stronger or weaker? These numbers are the bond strengths. The bonds we made are stronger. By how much are they stronger in terms of a number? They're stronger by 20 kcal per mole. This was kcal per mole, right? Yeah. Everybody agree they're stronger by 20? So if they're stronger, do we now have a more stable arrangement of bonding over here or less stable? More stable. And if it's more stable, did we have to put energy into it to make it more stable? Or did it give off energy and became more stable? It gave off energy. That's why it became more stable or lower in energy. So if it gave off energy, is your number positive or negative? Negative. It's negative 20.
So
Now you can do it like the equation up there. But do you understand why it's negative 20 and not positive 20?
so the bond strength inverse to the potential energy, and they're both in joules?
This side's more stable. Everybody agree this side's more stable?
Yes.
There's your bond strength. This has stronger bonds, right? I mean, all the others, we're just dealing with what was changed. All the other bonds are the same. Stronger bonds, more stable. More stable means lower energy. If this is lower energy than that, where did the extra energy go that this had? It was released. So if we show over here, we get that plus what? We get that plus the 20 that used to be in here. Exothermic. Now I said plus 20, but delta H is minus 20 because delta H refers to the system, and the system has lost 20 because this 20 goes into the atmosphere, heats the atmosphere, heats your room or something. Okay, so delta H is minus 20. And yes, if you want, you can just do that and get minus 20 and not even think about it. But I hope you would think about it, because maybe you're asked this question in sort of a context that's not just plug and chug, and you're like, okay, I've never thought about that. Okay, what about the entropy term? Let's go back over here. So, in terms of thermodynamics, is this reaction favored? Yes, because delta H is negative. And up here we said negative delta H is favorable. But you already knew that from Gen Chem, right? So it's favorable by thermodynamics. But is this reaction favorable by entropy? Aaron, you say no. Why is it not favored by entropy?
It's negative. The change is negative.
It's more order.
I'm too simple. What do you mean by negative?
Yeah, there's more order. It gets into.
It's getting more order. And nature don't like to get more order. 2 molecules going to 1, that's against nature. Okay? You ever seen a busted vase come together and reform? Okay? Things towards disorder. Okay? You ever seen a kid's dirty room all of a sudden just come together? No, it goes the other way. Clean room gets dirty, messy, disorganized. Okay? So it's favored by thermodynamics, but not favored by entropy. What is it? What's the ultimate answer then? Let's go back to Gibbs. Because remember, those two come together to give you your overall answer and get a delta G. We quantified this. We did not quantify this. The ultimate answer comes, well, how much is it? How much is the entropy? Maybe the entropy is so bad that it makes the thermodynamics just not count. But look at this. T Temperature magnifies this. So let me ask you this. Since we're talking about entropy, would heating help this reaction?
Yeah.
Oh, yeah.
You're talking, why would heating not help this reaction?
Because entropy is negative, so the higher the temperature, the less effect it will be.
Because temperature magnifies entropy. And if your entropy is bad, why would you want to supply heat and magnify the bad term? If you magnify the bad term, you're going to make the overall delta G more bad. Heating this reaction doesn't help. You actually want to do it at the lowest temperature possible. You got to do it with enough heat to get over the activation energy, but you don't just want to heat it very high. You're going to make the entropy become magnified. Do you understand magnifying the entropy? What we're talking about? So, we're working for a chemical company, and they're like, "Oh, let's heat this reaction up. Let's get it done in faster." You're a bit like, "Hold on. I don't think we should heat it." Okay. All right. Got your calculator? Here we go. Tell me this reaction is exothermic or endothermic. Favor or disfavor? Exothermic, talking about heat. Talking about heat, delta H. Talking about delta H, you can quantify it. You can do a calculation. That's your delta at your table. Because heat relates to bond strengths. There you go. What's broken? What's formed? What's delta H for this reaction? Do that real quick. Okay, what's broken over here?
Okay, FF.
See, there's an H here. The H is now gone. CH is broken. That H is primary, secondary, tertiary. It's a tertiary CH, and it's also sp3. What else is broken on this side? FF. Are those in the table? Somebody got it? What's the CH do we want to use? I reckon these are all your CHs. They're all sp3.
Looks like
That one.
That's a tertiary CH. So what we got? 97. This is all kcal per mole. What's FF? 38. FF is a pretty weak bond. That's one reason why F2 is so reactive. Okay. Anything else broken on this side? You have it in front of you. That's it, right? So what does this add up to? Let's see, I didn't memorize that one in. And I do not know how to do it add. So what is the answer?
135.
135? You memorized that one in 7th grade? No, we know how to do the mechanism for that math problem, right? Okay, so 135 kcal per mole, that's kcal per mole, right? Broken. What's formed?
tertiary CF or ACF.
We've got a CF. The carbon is tertiary. I don't know if that's going to matter in the table. Some tables are not really complete. What else is formed over here? HF. What's HF? Around 130? 136? Is there a tertiary CF or something?
There's no CF.
Not a tertiary one.
Is there a regular CF? There's only 115?
They don't seem to change for all the counties.
That's all we have in the table. That's all we can do, okay?
There's a tertiary CBR.
We need to stick with CF because changing the halogen really will change the bond strength. CF is very strong compared to the other halogens. I think we need to go with that. 115, is that right? What is this? 5? 251 formed. What's the difference in the two? What's that, 65? 6, what is that, 116? That's the difference? Is it positive or negative? Which side is stronger? Left or right? Did we make stronger bonds or weaker bonds? Stronger. Are these more stable or less stable? More stable. Is more stable higher energy or lower? It's lower in energy. So now it's lower energy. So where did the rest of the energy go? It released plus 116 kcal per mole. This is what you can write on the right side. This is almost like a product. Okay, and so it's exothermic. What is delta H? Delta H is negative. It's negative 116. Okay? That plus means it's on the right side. Shana, we're going to get what? I was just adding these up because it took 65 to get to 200. And then 51 more, gave me 116. I was just adding.
So this is going to be the energy it would take to remove them two completely to infinity? Is that the bond strength? Is that what we're talking about?
Bond strength is the amount of energy it takes to break the bond. It takes more strength to break those bonds over there, so those bonds are stronger. Stronger equates to more stable equates to lower energy. The system went to a lower energy. Where's the rest of the energy? Well, it can't just disappear, it's released. Since it's released, delta H is negative. So is that reaction favored thermodynamically? Yes. Because delta H is negative. Okay. Is it favored by entropy? Is it disfavored? It's sort of a wash. 2 molecules going to 2. Entropy is like not that important unless you really get into quantifying it on a more microscopic level. Okay? Now, repeat that reaction using iodine. Do this on your own. You'll see a big difference. Why the difference? Okay? Basically do that on your own. We can see if there's any questions about it.
So if we were to do,
You should also go back and do this here. Okay? Now you should be able to do this. Which reaction gives off the most heat? This comes from your calculation. Okay? Endothermic. Fastest. Fastest has nothing to do with thermodynamics. Fastest is a kinetic consideration. Let's look at kinetics. Kinetics is the rate or speed of the reaction. Depends on the activation energy required for a reaction. We'll see more of this. Here are two reaction coordinate diagrams, okay? We showed one yesterday. And here's some examples. Very generic. This is reactants going to products. How many intermediates in this reaction? None. Remember, the intermediate was a well, okay? What is this here? That's just a transition state, okay? That's all that is. There's no intermediate. There's no discretely formed intermediate. And this is your what? Activation energy. Okay? This is just the energy of your products. Products are more stable. That means they're lower in energy. So this reaction was exothermic. Okay? Now they're doing delta G. I'd rather do delta H, because when you do delta G, that means you're also considering entropy. But I don't know how you consider an entropy here when you don't even know what the molecules are, or what the reaction is. Okay? So it's kind of over generic. On the other hand, we can have something that looks like this. This would be endothermic. Here the products had to gain energy. That's endothermic. It would be positive delta H. Okay? We can look at some reaction coordinate diagrams down here. And we can ask the question on the right. Which reaction is most favorable? Of these four, which is most favorable? Anybody want to clarify that, ask for a clarification of that question?
That's the greatest one. So what's the clarification?
You might want to say, or do you mean favorable by thermodynamics or entropy? Well, again, entropy, we'd have to know the molecules. We don't even see those. We're talking about thermodynamics. Which one is most favorable thermodynamically? Certainly not this one, because that's endothermic. That's endothermic. It's one of these. And it looks very close, but this is more exothermic. It's going to be more favorable thermodynamically.
So even though, in terms of being favored by thermodynamics, all you're looking at is like how much, or how exothermic it is, not the activation energy?
When we did these calculations, we were doing thermodynamics. And what did we look at? We looked at the difference in the numbers, and we said that this was 116 more stable. That's like being 116 lower in energy than here.
Okay, so you don't
Did
take
we look-
activation?
Did we look at activation energy here? No.
Okay.
Activation energy is related to your kinetics or rate.
What, just the term favorable in general would say, like, you can make an activation energy so high that it theoretically would never.
That's why I said, do you want me to clarify the question? And then I clarified it and said, mainly we're saying thermodynamically, is it favorable? Yes. Reaction of diamond with oxygen is thermodynamically favorable. But why does a diamond not just spontaneously react with oxygen? Because the activation energy is so high. Thermodynamically it's favored, but kinetically it's not. So yeah, you're right. But again, this is really a thermodynamic question. Which favorable reaction is fastest? So which two are favorable? These are favorable. Which one's going to be fastest? This one. Why? Because fastest, you talk about activation energy, and this has the lowest activation energy. All you need is to get a little bit of energy to get it over the hill. This one, you're going to have to put a lot into it. Let's see. That one's actually faster. But this one's more exothermic. Because fast and exothermic, there's two different considerations. Kinetics versus thermodynamics. The reaction of diamond with oxygen is very exothermic. But it don't happen. Because the kinetics are too slow. Okay. Y'all saw all this at Gen Chem, right? Saw this review of Gen Chem, right? What's different?
It's, 2 steps.
Nothing. Have an intermediate here? Okay. Let's look down here. Now, talk about intermediate. This reaction has an intermediate, right? See this energy well? Here's intermediate. This is actually an alkene reacting with HBr. What's the first step? Pi bond reacts with H+, leaving a carbocation. What's the next step? Halide attacks carbocation. So here's your carbocation, okay, intermediate. This is exactly what I drew yesterday, right? That's what I drew yesterday. Exothermic because why? We can qualitatively assess this. You can get out the table, but what's broken here? Pi bond and HBr, but mainly you can get pi bonds broken. What's formed? 2 sigma bonds. Which is better? Which is more stable? 1 pi or 2 sigma? 2 sigma is more stable. Sigma bonds are more stable. So that's an exothermic reaction. You can just assess that qualitatively, or you can do it quantitatively with a table. How many transition states are in this? We did this yesterday, right?
2.
2. A transition state leading to the intermediate and a transition state leading to the final product. Here's some other. We also did this yesterday. Now let's get it back out here. Why, when this reaction occurred, did it not give this and the Br ended up on the outside carbon? Because this would involve, if the Br is here, that means the cation was there. Because for the Br minus to add there, you had to have cation and these electrons add there and you get that. But why does the cation not form? To get this cation, that means where do we ultimately add the H? Where's the new H at?
Yeah.
See it right there? That's not a cation, it must be 4 bonds. So this reacted, we pulled these electrons away here, okay? Making the new bond to H, leaving that as a carbocation. Why does it not happen this way though? Because up there, this is the primary carbocation. Up there, we made what type? Tertiary, which is better, tertiary or primary? Tertiary, because tertiary has more induction. Then I tried to show you at the very end, but this is basically explaining that right there. And it's actually the same cations. This cation is more stable, and thus it's going to sit at a lower place. And when this reaction takes place, it's going to go this way because energy doesn't go uphill. It's going to take the least resistant path. It's like water running down the road. Okay? If it comes to a fork and one road goes like this, the other road goes like this, both going up, which one is the water going to go up as it's flowing through here? Don't go up this road. If you see the water go up this road and not this road, let me know. I want to see it. Okay? You may get a little splashing up, especially if it's come big hurricane. But mainly going to go up the least resistant pathway. What do we have down here? Okay. Well, one thing we need to say up here is, typically, what this illustrates is, this is the intermediate, that's the transition state. The lower energy intermediate typically has the lower transition state leading to it. And we typically just kind of say that always. Lower intermediate, lower transition state. But that's not always the case. There's an exception to that we'll usually state. Down here it shows an exception. You can look at this, all the details here. The main thing I want to point out is the second step. This species is more stable. This is lower in energy. And it's called the 1,4 product. We'll actually see this here in test 3. And I'll show this right here again. And usually we say the more stable product has a lower transition state. But is that the case here? Here, the lower energy product has a higher transition state. That's an exception. Okay? What do we have below? Really nothing new. You can just look at these. How many intermediates in this reaction? None. You just got a transition state. No intermediate. We'll cover SN2 reactions here in test 3. Okay, I tried to go through that pretty quickly. Any questions about that? Please do the front page and the iota question. Okay. Any questions about the first page over here? Regioselective, what does that mean? Well, up here we showed the reaction taking place and the Br ended up bonded to the tertiary carbon. Down here it's bonded out here. Not here, but it's bonded to a different region of the molecule. And so regioselectivity is just a term to describe that. If I do a reaction and the bromine ends up bonding to this region of the molecule versus this, we say it's regioselective for this region, selective for this region. Okay? It's just terminology to allow you to describe a reaction. Because if you do this reaction, you get predominantly the top one. Now, in the context of a reaction, it's called regioisomers. That guy and that guy are regioisomers. Regioisomers are just constitutional isomers, but you call them regioisomers when it's in the context of a reaction. And you say, hey, look, this isomer was formed selectively. You call it a regioisomer because okay? It's just a constitutional isomer. Regioselectivity. Why was this reaction regioselective? Because of the carbocation stability. We've already said that a couple of times. Primary carbocation not as good as tertiary. Here's your carbocation stability. We should know why. The more carbons attached to your positive carbon, the more induction. The worst would be a carbon with no carbons attached. That's not even considered a primary. That's just sort of the parent. That's the worst. Now, all of these are originally sp3 carbons. Once it becomes a carbocation, what's a hybridization? What's the hybridization of the carbon as a cation? It's now what? Joe?
SB2.
Now sp2. Okay? But originally it was sp3. And now it's trigonoplanar. And if you graph that hybridization, you would see an empty p orbital. So you can see 3 hybrids making 3 bonds, p orbital left over, but it's empty. And it's these electrons that are really going into this empty p orbital. But as it happens, it undergoes rehybridization. Now, that was just a glimpse into that big book. Okay, and we're not going there quite as much. Okay. Predict products here. Tell if the reaction is regioselective or not. So alkenes react with HX to give an addition product, where you got an H and an X added across the pi bond. What's the product here? Somebody got it? Should have done all these or tried all these.
Add HCl to the tertiary.
You're adding what to the tertiary carbon?
Add the Cl to the tertiary carbon. Break the.
Be that product right there, right?
H be attached?
We typically don't show H's on non-bond structures.
Okay, even if it's the new one? I thought yesterday you were saying the new one.
I mean, even if it's new.
Okay.
If you're gonna show that molecule, there it is.
But if it's regio selected, you need to show it.
Do what?
If it's regio selected, would you need to show the H?
Why do you need to show the H?
No, if it's regio selected, right? 'Cause you-
It's hard to draw a perfect hexagon. How many H's are there? We learned this on day one, or what, how many H's there?
2,
Two. I mean, there's 2 H's there. How many there?
1,
Where'd the other H come from?
ACL.
ACL added across the punctum. I mean, right? You gotta see the H's. If you wanna draw it in, be happy to, but typically when you do line bond structure, you don't draw in H's.
Even if it's a sin or anti-addition,
Even if it's what?
it's a sin or anti.
No, there's no reason to draw it in. If I asked you to draw that structure last week, would you have drawn in the H's? Why draw it in today? But that's a big thing, because I know you guys get all confused because you're like, well, where's the H? The H is there, right? Okay, why did we not get that product? Because mechanistically, if we think mechanistically, what was the intermediate here? What's the mechanism? I'm just going to show this ionic, okay? Because this likes to become ionic, especially if you put it in a polar solvent. You can do it either way. What's the first step?
The pi bond attacks the.
It hinges, okay? It's going to go in and make a bond. But is this going to come down, leaving that a carbocation up there? Or is this going to hinge up, leaving carbocation down here? Where are you going to make carbocation at, top or bottom? Top. You're going to make it at the top. So we're going to hinge down, and we're going to get new H added here. And now what's up here?
CO.
Well, mechanistically, this is our intermediate. What do we put here?
Positive.
Positive. There's only 3 bonds. So there's your carbocation intermediate, okay, transition state leading to it. What's the next step? Then the Cl minus adds to the carbocation. And when he does, what do you get? You get that right there. Do we make carbocation down here? No, that would be secondary. We make tertiary carbocation. Because we don't make carbocation down there, we don't get chlorine adding down there. Is this reaction regioselective? Do we get the chlorine bonded in one region versus another? Yes. We get that one, not this one, regioselective. Okay? We only get this regioisomer, not that regioisomer. So ultimately, what's the decision here? Where are you going to make carbocation? Because wherever you make carbocation, that's where the chlorine is. That's how you predict the product. Okay? So what's the product down here?
That I would be on the peak of the double bond.
Boom, boom, boom. That's supposed to be a boom. Boom. Iodine here?
Yeah.
Why is the iodine there? Because carbocation is going to form there. Why is the carbocation formed there? Because this hinges away from this. Okay? Here it is. It goes attack, leaving that carbon over there plus. Why that one plus?
Secondary.
UH there plus here. And then the iodine in the fast step attacks there and you get the product. We're not going to hinge this way and leave cation out there on the end as a primary carbocation. So is this reaction regioselective? Are we going to get the other regioisomer? No. Regioselective, check. That was also regioselective. Okay, let's look at the third one. What's the product down here? Are we going to make cation on left or right?
Either.
Either one.
Left has more donation potential.
Well, when it's a long chain, it's typically kind of a wash. Okay?
So both-
Only when you have like branching coming in. Let's show the two possible cations. We can make that cation, or we can make that cation. Which cation is best? They're both secondary, and so it's like they're going to be both equally formed. I mean, if you drew them on a reaction coordinate diagram, you'd put them at the same level. There's no reason, okay? So this is going to be both regioisomers. Iodine is going to attack either one. Is this going to be regioselective? That is, are you going to expect predominantly one product over the other? No, there's no reason to expect that. Now, it depends on what you mean by regioselectively. Is 51 to 49% regioselective? Actually, that is. But for us, we're looking at kind of a predominance. This is going to be basically 50-50. Question, Zach?
So if you were to put that into HI, it would make two different molecules, right?
It's going to be two different molecules. There's going to be no reason to predict one over the other. It's not a regioselective reaction. The top two are. Especially based on your theory. Okay? Synthesis. Okay, this is our first look at synthesis. All right? Basically going backwards. Provide a high yielding that is a regioselective synthesis. You don't want to propose a synthesis that's going to give a mixture of things. You would like your synthesis to give only that. So you want it to be regioselective. Okay? So when you talk about synthesis, you have to say, okay, what type of molecule is this? It's an alkyl bromide. How do you make alkyl bromides? HBr reacting with what? An alkene. Okay? Alkenes react with HX to give alkyl halides. That's sort of your starting point. Okay? And you'll do plenty of reactions in organic chemistry. Okay? So you've got to be able to organize your thoughts and what are you doing, material. So if you want to synthesize this, you're going to propose an alkene and HBr. Now later on, you'll know multiple ways to make this, but right now you only know one way, alkene and HBr. Okay? So we're going to have something reacting with HBr. All right, we'll show the alkene. Show the alkene, and you can name it if you want. What's the alkene going to look like?
It's from 1 to 2.
Which would you rather use if you want to make that in high yield? I mean, this could react, and we could make cation here, and be our attacks there, and that would get that product.
But it's not regioselective.
But it could also make cation there. That's not going to be reaching. Is this only going to give that product? Favor secondary. Okay? That one, that's going to give you your better yield because that's only going to give one product. This is going to give you two products. Okay, do the one on the right. Reacting something with HCl. It's the only reaction you know so far. that product doesn't have stereochemistry. Why don't I put the double bond there? Is that reaction going to be good for regioselective?
Yeah.
But you could put it on that list.
Somebody got another starting material? You could also react it with either one would be good. Anybody realize that one?
You could also react it with the stereoisomer first, or is that?
First one doesn't have a stereoisomer. It brings up a good point. You mean the alkene stereoisomer?
Is that not, that thing wouldn't be either a wedge, that methyl group on the top there?
You what?
That's either a wedge or a,
No. That carbon is sp2, trigonoplanar. It's all in plane the board.
oh, okay. That makes
Neither one of these have stereoisomers. You could call this Z, and I did tell you if you could do Z, there should be an E. You can't do an E there. You could not have this bond be trans and still have a ring. So you got to be careful about that. There's no stereoisomer there. There would have to be a big ring for that double bond to be essentially trans in the ring. Either one of these would be good. Everybody understand that? Where are you going to make cation, left or right?
Left.
Left. Where are you going to make cation, top or bottom? Does everybody see that this is the same intermediate? This is actually the same intermediate.
Are you breaking different bonds here? One of these would have favorable intermediate rate.
Both of these give that same intermediate. Everybody see that? Which reaction is going to be more exothermic? Reaction A or B?
Same.
Which is going to be more exothermic?
Secondary, secondary.
Depends on.
Shelby? A or B, which would be more exothermic?
I don't know, I was trying to figure that out right now. It would have to be the one that has the stronger bond rate before.
No, it would actually be the one with the weaker bonds. So if we do a reaction coordinate diagram for A, I'm going to do it very abbreviated. We would say we go here, there's an intermediate, and then we get the product. Okay? Do it very quickly. It's all on tape. Okay? If we do B, it's the same product, it's the same intermediate, but does B sit the same as A? Which one's more stable? Yesterday was only 24 hours ago. Which one's more stable? The one with the double bond having three substituents, or the one with the double bond only 2 substituents? It's more stable. It's more substituted. Since it's more stable, where are we going to draw it here? Lower in energy. Okay. So when A reacts, we have this much energy released. When B reacts, we have this much energy. Which one's more exothermic? The one that's set higher to begin with. Reaction A would be more exothermic. After I did that, do you see how the answer was ultimately kind of very straightforward? Yeah? The considerations we did? You just had to be kind of told how to, the thinking process. Did everybody get there?
Why would A be more exothermic?
Yeah, the more stable means the less energy, right?
It's the more.
I'm sorry, I called that one A. Okay, that's why you didn't understand it. It's actually, I was calling these reactions. That one's more stable, so A sits here, and B is here. B is more exothermic. Is that what I said? Well, check and take. All right. Now this is look, all the considerations, okay? And a lot of times organic chemistry is like that. All you gotta do is just, instead of considering one thing, you gotta consider 4 or 5 things. But they're all very simple. Add it all up. Does everybody see why B is more exothermic?
So in a problem like this, if it said, like, draw the synthesis to accept both, like either or.
Either one. They're both good.
They're using more stable than you first.
We would want the more exothermic one.
Well, reaction B is more exothermic. I didn't ask you anything about that. Either would work for this question. Either one of them is a regioselective. The exothermic was just an additional question to go back and just look at some other previous stuff. I just kind of added that on. That was extra, that was free. Okay? Down here, which product is favored in the following reaction? Ultimately, what's the question here? Ultimately, the question is which cation is going to form. Ultimately, the question is, are we going to make cation on top or bottom? Ultimately, the question is, are we going to make this cation or this cation? That's ultimately the question.
Top.
Because if it's that cation, then we get product on the left, BRS there. That is tertiary. And this is what?
Secondary.
That is secondary, because that's not a carbon. But you gotta be, there are other things that stabilize cations. This is actually the more stable cation. Why? I know Utah knows, because Utah likes,
I do? Okay.
Utah likes resonance. You seem to like resonance, because you asked about resonance several times. Resonance! What's hybridization of the cation? We asked that earlier, and it's sp2. With an empty p orbital, right? If you graph that, you would have three hybrids, all with bonds, and then the p orbital. What's in the p orbital?
Nothing.
Nothing, it's empty. Okay? So what's hybridization of this oxygen?
SP2.
Lauren? Taylor?
If it had a double bond, I would think sp2, but
What's hybridization of
it
this
would
oxygen?
normally
Elena?
be sp3.
Would be SP2.
It's also sp2. Why is it sp2? Because anytime a lone pair is next to a p orbital, a lone pair is going to want to be in a p orbital. Did we say that? Right? Did we say that?
Yes.
Okay, if we draw the orbitals, there's an empty p orbital there. That's the cation. This oxygen is over here. One of the lone pairs is there. The other lone pair is there. You see trigonal planar with the bonds? What is this lone pair doing?
Conjugate.
It's conjugating. Now what do you call it when p orbitals conjugate? Resonance. Okay? And these electrons are really helping this cation. Okay? This is resonance. A resonance stabilized carbocation is a great thing, and it's better than a non-resonance stabilized. Resonance, this p orbital overlap is it's akin to almost bonding. And we can actually show resonance structure where we take these electrons and we just move them in, and we show an alternative Lewis structure. I'll try to write big and clear this up a little bit. What does this arrow mean? Electrons moving in to make double bond, O, one lone pair, and now the plus is there on oxygen. And now we have delocalized the charge. The true structure is somewhere in between, partial plus, partial plus. It's going to be a resonance stabilized cation, that's going to be best. And so since the cation is formed here, that's where Br attacks, and which one do we get? We get this.
So is Br then less likely to get attack it since it's more stabilized?
It is less likely to attack it. But then what's the relevance of that? Go ahead.
I don't know if I had any relevance.
Okay.
It still has to be-
Let's think about it. The question was, is Br less likely to attack it because it's more dispersed charge? Yes. But the Br attacking it, is that the rate determinant step or the fast step?
Fast.
That's a fast step. So the fast step is not going to be as fast, but it's still going to be the fast step. And so ultimately, it doesn't matter. Changing the fast step doesn't matter.
So here, even though we have a dominance of product, the other product gets possibility as well.
It's just like, in terms of theory, no. This reaction should be regioselective. It should only give the one on the right. Your argument is because this is a more stable cation. Why is that more stable? Because it's resonance stabilized. That's only stabilized by induction. Okay? This is only through single bonds, induction. Resonance is a stronger effect. Everybody understand the hybridization here? We did all that last week. And then when I drew the orbitals, that lone pair, why would this lone pair want to be in a p orbital? So it can interact with the one next door? That's a good thing. And it's actually more powerful than this. Question?
So if you put a less, sorry.
Is there a question back here? Go ahead. We need
So
to
if there was a
move on.
less electronegative, if you put sulfur there instead of oxygen, would that make it even more stable since it's carbon or it's not hanging on to the electrons?
Sulfur is more willing to donate because it's less electronegative. Sulfur is more willing to take on the plus charge. Yes, it'd be better with sulfur. Aaron?
So, is it a general rule that resonance trumps tertiary carbon?
Yes. Generally. I can maybe give you a situation, I can always give you an exception.
Yeah.
Resonance is typically better than induction. Just like hydrogen bonding is better than a dipole-dipole. Okay? That's about the fourth or fifth time we've seen resonance. We'll see it another 10 times and then we'll finally cover resonance. Okay? But when we cover it, we'll just really review it. It's a building thing. All right? If you're not working and going ahead, when we get to it, you'll be way behind. Okay. Let's look at, make sure we are, if you need to go, I'm going to keep going because we got to keep up good pace. Days that I feel like we're doing good pace, we'll take a break, but I don't think we're doing good pace right now. Let's, we'll cover our outline. Yellow. Okay. Let's make sure we covered. Did we cover everything here? We got carbocation, electrophilic, cation or species. Okay. Any questions about these things here? Go back here, what did we just cover? We just covered this reaction with HX. Okay? It'll be any halide, typically not HF. We may say at some point, why not HF? Next reaction we're going to look at is a reaction with H plus in water to give alcohols. All right? And when you do this, it's called a hydration reaction. When you add water, it's going to give alcohol. First off, there's no reaction with an alkene in water. Alkenes don't react with pure water. The skin of an apple is largely composed of an alkene. Okay, when it rains, does the skin of an apple react? No. It actually protects the apple. Okay, it's actually hydrophobic. But maybe if we have some acid rain, it might do something. Requires an acid catalyst. So we have water and H plus catalyst. Then we can get an addition reaction, addition ultimately of water. A lot of times this is written out as H2O and H plus, but it's how? It might be written as H3O plus. That's water and H plus combined. All right? What are your H plus catalysts? Usually sulfuric, phosphoric, HF. Okay, there may be others. But not HX, not HBr. You don't want to use that as catalyst because HBr reacts with alkenes to give alkyl bromides. You don't want your anion to be nucleophilic. Sulfate will never add to a cation. Phosphate will never add to a cation. F minus will never add to a cation in this class. But Br minus and Co minus and I minus will. So you don't want your catalyst competing and giving you an alkyl halide. Mechanism. I'll do this one out for you. The first step is no different than the previous step. The first step is reacting with the H plus. In the previous reaction, the H plus came from the HBr. Because HBr is a strong acid, so it supplies H plus. Water doesn't supply H plus. So we have to bring that in from some other place. And we bring it in from like sulfuric acid. I'm showing that ionized, just monoionized, H plus bisulfate minus. The alkene sees that H plus and it attacks it. Are we going to make cation on left or right? Left or right? Lucy? Would you rather make carbocation on tertiary or primary? Tertiary, that's left, okay? There it is. So these electrons hinge away from that carbon, go attack the H, leaving that one as a carbocation. All right? Nothing new there. At this point, here's your intermediate. Something attacks it. I told you that that's not going to attack. We don't have a halide to attack. But we do have water, and water can attack. And so these electrons add, what does this arrow mean? These electrons making covalent bond to this carbon. There it is. Only one lone pair remains. That's it. This happens to be a positive charge. We don't lose an H. That's it. Nucleophile. What's a nucleophile? Something that loves the nucleus, something that loves positive charge. See, these electrons love positive charge, so we call that a nucleophile. This likes electrons, so we call that the electrophile. Okay? We can say that this is a nucleophilic addition to the carbocation to give this. This is not final product though, because we have to lose an H from the oxygen. What can take an H? The bisulfate anion. Now here I'm showing it condensed. I'll typically do that. Now if we want to show that out, it's this, and these electrons take an H. That's just an acid-base reaction. We did that last week. And when that takes an H, what do we get? We reform sulfuric acid, and we get our final product, alcohol. These electrons move on to oxygen, now 2 lone pairs, there's your final product. Hopefully you see the similarities between the previous reaction, but here the nucleophile is water. And thus we end up with an alcohol. We reform sulfuric acid, so the catalyst was reformed. Questions? You, Tom?
If we use concentrated H2SO4 itself, aqueous within the HSO4 negative attack, is that happening?
Not in this class, it won't. Which hopefully means to you that it can. But not in this class. Sulfate will never attack anything in this class, we'll get it to with me. Alright? Sulfuric acid is just an H plus source. The anion will never do anything. Now, strictly speaking, you could use water to take the H, and if water took the H, you would form the alcohol plus what? H3O plus. But that's how sulfuric acid exists anyway. Sulfuric acid is H3O plus. I like to form the actual acid, like sulfuric acid. So I use the anion. And also, this is drawn out full, lone pair taking the H. That's just an acid-base reaction. Does everybody see this is just like the acid-base mechanism I gave you last week? Okay. Typically though, moving forward for time, I'll just show this taking the H. Question?
For that
Is it,
H-
Sophia?
Yes. Coming off of the right on the first part, is that H still on the second?
Coming where?
Right there.
Right where?
That H, is that still on the next one?
How many H's on this carbon? 3. How many on that carbon? 3. I just drew in the new one. It's still there.
So that's the same thing then?
It's still there. Okay, sometimes I'll draw the new one, sometimes not.
Okay.
Okay? I just showed you where the new H went. I mean, there's 2 other H's there. Now, if I make this a charge, then there's only 1 other H there. But that's not a charge. Now, all these reactions are reversible. You can actually take an alcohol, react with sulfuric acid, and you can dehydrate it to the alkene. That'll actually be test 3. A lot of these reversible reactions. That's not an addition reaction. What do you call this? That's an elimination reaction. You eliminate water. Ultimately, what do we add to the alkene? We've added that and the new H. Everybody agree? Now, what do you call H and HO if it's all together? H2O. We've added water to the alkene, but the alkene didn't react with pure water. We had to add that acid catalyst to supply the H plus at the beginning, because water doesn't supply H plus. Predict the products down here. Hopefully you see it's no different than with the HX, except here the nucleophile is water, and you end up with an OH on your as the nucleophile. Okay, I said OH. A lot of times you guys will start showing hydroxide because you think that that's where this came from. It came from hydroxide adding. Did hydroxide add to the carbocation? No. Are we under acidic or basic conditions? Acidic. You do not have hydroxide under acidic conditions. Water adds to the carbocation, then you lose the H to ultimately end up with an OH. Okay, show products down here. We're going to make cation over left or right? Left or right? We're gonna make cation on left. What's gonna add to cation?
H2O.
Water, and then we're gonna lose an H and ultimately have this. Okay, make that right there.
I have a question.
That alcohol. Question?
For the intermediate for that, if you do it like the step by step at the top, and when the water attaches, you have the two H's. Because in this one, H plus in the catalyst, did that H just come off, or what causes that H to come off?
Right up top, something took it. What takes it?
The top one is the HSO4, and this one that we just did.
The H.
What else did I show taking it up there? I showed an alternative. Instead of bisulfate taking it, I showed
Water.
water taking it.
Oh, okay.
And if water takes it, you reform H3O+, which is essentially your acid. You reform your acid.
Okay, so just another water
Yeah.
molecule took that? Okay.
Now, see, I showed this very generically. There's got to be a minus here.
Mhm.
I mean, there's got to be like a Cl minus. Well, you don't want Cl, that'll you end up with an alkyl chloride. I mean, there's got to be something minus here. And whatever that minus is, you could show taking it.
Okay.
So, but you have to be able to deal with generic.
Okay.
And you show water taking it, so you'd make your product plus, when water takes the H, you reform H3O+.
So whenever the H is going on to the, is taking those, where the electrons are grabbing that H from the alkane, what's actually happening since it's existing as H3O+? Is it grabbing a H3O+ ion and the water falls off? Isn't the H+ really existing as H3O+?
Yeah, H+ really doesn't exist. The H+ is associated with the water. Yeah, H+ doesn't exist.
So whenever it does go on there and the H attaches to the, what was formerly the alkene, then it just, the H3O+ attached to it and the water drops off.
The alkene attacks the H, the water, yeah, just like the alkene attacking the H and the Br leaving. Okay. Product down here. Somebody got a product down here? Ah, what's this? This is not water, that's ethanol. HF, that can be used as the catalyst. What's the product down here? Product down here would be this ether, right? Questions about that one?
This is an ethanol liquid.
Questions?
Can you show
Okay,
the
don't-
mechanism for that?
Show the mechanism. Very good question. I could ask you to show the mechanism. Tell me the mechanism. What's the first step?
The double bond breaks.
What is the double bond attack? Here's a hint. Double bonds have only attacked one thing so far in this class. What is the double bond attack?
The H.
H+. Where's the H+ coming from? HF is a strong acid, fairly strong. Right here. It's your H+ source. That's your catalyst. Okay? And so this attacks here. Where do we leave carbocation at? Right here? Okay. There's a new H there, carbocation here. Okay, what attacks the carbocation? Does F- attack? No. That's why we use these up here. I told you, none of these will attack. None of these anions will attack. Okay? Since that won't attack, what's going to attack? All right? Lone pair. These electrons attack cation. What does that give? We now have what bonded to this carbon? Oxygen. How many lone pairs left on oxygen? One, because the other one is now bonded. What else is on the oxygen? H and a An ethyl. H and ethyl. That's a positive charge. Okay. Now you're going to reform your catalyst. That's what I told you up there. Reform the catalyst. So what's going to take the H? F minus. And so these electrons take that H. These electrons remain on the oxygen. And when that happens, what do you get? 100 of it. Now there's 2 lone pairs there, plus what? What else is here? Plus HF reform. Okay? That's your catalyst. But I told you up there, HF could be a catalyst.
So what exactly went into a container?
So once we did the mechanism, you see that's what you get. Happens to be an ether. Where did I tell you we get an ether? I didn't. But it's all here. Does everybody see it's all there? Because what do you learn? You learn alkene attacks H+. You make the right carbocation. And then something's going to attack it. What's going to attack it? Well, I told you this doesn't. That's the only thing we can. There you go. You learn mechanism.
Question, sorry, question.
We need to sort of move on a little bit. Questions are great. We've got to keep up a good pace. Some of these questions after class, office hours, anywhere. And I hate to do that, but our time is limited and we've got to cover material. So in some cases, I'm going to plow ahead, okay, guys? Okay, important thing back up here, stereochemistry. Keep asking. If I just move ahead, that means I don't want to take the time. I love your questions. Okay? Please keep asking. Up here, stereochemistry. Let's take a bit and look at this. Later on, we're going to call this a chiral carbon. That's tetrahedral. Is the OH going to be forward or back? Forward or back? These are different. Which one's it going to give? Well, guess what? There's a mechanism for predicting this. So let's back it up and let's ask, how did we get to that point? We had this cation and water attacked the cation. Okay? What's the hybridization of the cation? sp2. What's its geometry, Brown? Trigonoplanar. There's an H there, right? Okay? I know there's an H there. It's right there. It didn't disappear. It's right there. Trigonoplanar. Planar means it's plane of the board, okay? It's flat like this sheet of paper. All right? So let's do it like this. Here's the cation. There it is, okay? Walking around. All right? Walking around. Now, you're the water and you attack it. Which side are you going to attack from? Probably the side you're on. So you attack. Okay, you attack from the right. Now you attack it. Which side are you going to attack from? You attack. Okay. Which side? It's 50-50. Either side. Okay? It all depends on, okay, you got a gazillion molecules. Some attack from this side, some attack from that side. Now here, if it attacks from this side, which one are you going to get? Here. Because if you attack from this side, you're going to be bonded from that side once it becomes tetrahedral. This is where it attacked from the back. It's a 50-50 chance. Okay? It's going to be 50-50. And we're going to call that later racemic. Alright? But it all is because your intermediate was planar and it can be attacked from either side. It all depends on how it approaches. but it's all gonna be random because you got a gazillion molecules. All right? Now, as usual, that right there will be used many times going forward, and you'll use that to predict other things. Any questions about how you attack a planar turbocation? Okay? Hopefully pretty straightforward. Now, this guy down here, there's no stereochemistry. There's no stereochemistry down there. Yes, it is tetrahedral. Okay. We have carbocation rearrangements. One thing that carbocations are prone to doing, they're prone to doing it today, they're prone to doing it near the end of organic too. And that is rearrange. And this illustrates that. If you take this alkene reacting with HBr, where are you going to make cation? Top or bottom? Bottom. And since the cation's on the bottom, that's where Br should attack. But actually here, that's the minor product. The major product, the Br is, you may think over here. It's actually over here. How did that happen? What is the mechanism for this? So that's a carbocation rearrangement. The first step is nothing new. We're back to HX. We can show it ionized. Let me show covalent. There's a question about covalent. Okay, I showed it before. If it's covalent, we have a dipole. This could be an oxygen with H3O plus. These electrons hinge away, attack that, and these move over here. What does that give? Okay. We made a bond to H, leaving this as what? Carbocation. That moved on to the Br, and so we got Br minus. This adds here, we get the minor product. How do we get the major product? I heard methyl. I'm methyl. Let's back it up over here. Does everybody agree to get that product, we need that carbocation? Br minus, okay, yeah. How can we get that here? Let's see here. See, I hate drawing in the H because it makes you focus on that and then, okay. Can I get rid of that? There's a new H there. What's the difference here? How many H's here? One. One H there. How many here? One H on each carbon there. How about over here? How many there? Two. How many there? One. No, if there was an H there, it wouldn't be a positive charge. There's no H there. Ah, okay. There's no H there. If there was an H there, it wouldn't be positive. 1 and 1, 0 and 2. It looks like one H moved over here. Indeed, that's what's happening. This H here migrates or rearranges these electrons. Actually break away. Somebody grab my finger, break it away, and move it over there. I'm going to do it with an arrow. I'm going to break it away and move it over there. I'm breaking away the two electrons. Both electrons are moving over there. What does this arrow movement give? It gives this. What moved over? Obviously the H, but what do we call that H? Call it hydride, because not only did the H, how many electrons moved over? Both electrons in the bond. So it's like H here. And that's a minus charge, and what do we call H minus? What do you call Cl minus? Chloride. What do you call H minus? Hydride. This is called a hydride shift. Ultimately, the carbocation rearranged, because here the carbocationi's there, it's there. What type of carbocation is this? Primary, secondary, tertiary? Secondary. What kind is this? Tertiary. Why did it rearrange? Because it went to a more stable carbocation. Mechanistically, that's it. More visually, how is it? We got a CH bond here, and a carbocation over there. The sigma electrons are still electrons, even though they're bonded. They see that cation, they sort of are attracted over there. And ultimately, they just like, okay, see you later, I'm going. And they go over there and bond. There's enough attraction. What drives this? You're going to a more stable result.
So if that's the major one, and then the
And then how do you get to the final product? Now the BR attacks and you get this. Mike?
So that's 3-step, one is favorable over a 2-step.
Here's the take home. For me, anytime you can rearrange a carbocation to a better one, always do that, and that'll be your major. Ultimately, you have to do this in the lab and see what the outcome is. The question is, here's really the question. Is this going to attack here faster than it rearranges? It's hard to know. It may vary. That's research. For us, always rearrange when you can, and let that be your predicted product. So the predicted product here is the one I labeled as major. If I said show major product, you would show the rearranged product. Sometimes called a skeletal rearrangement. Comes from a carbocation rearrangement. All right?
So, can this chain reaction down a line that has like,
Can it rearrange multiple times? It could. Ultimately, if you can get a better cation, tertiary is better. Maybe from the tertiary you can move over to a resonance stabilized. Let's look at the one below. If you take this alkene, react with H3O+, looks like you're doing a hydration reaction, water and acid. Make an alcohol, cation on top or bottom? Bottom. You might think that water should add here, you lose proton, you get this. Actually, you end up with oxygen over here, and that's your major product. What's going on here? This was not a hydride shift. What? H plus attacks. UH there, plus here. Every reaction we do starts by putting the cation in the right place. Top or bottom? Bottom, secondary. Water can add here, that's how you get your minor product. You can go through that. What happened to get the other product? There's no H here to move over. What moves over? It's actually a methyl. These electrons break away. Somebody pull my finger away, okay? All right? We're yanking it away. What does that give? I'm not going to draw the H in again. Now what's on this carbon that moved over? Now where's the cation?
Left tertiary.
Is the cation here or here?
Left.
It's here. That's because how many H's are on this carbon? you gotta keep track of your H's. There's no H here, so how many H's there? Well, right there, you see there's one. That's one of the problems, guys, is you gotta keep track of your H's, because your skeletal, that right there gives you some trouble. You gotta know where your H's are. Here's the plus. All the time I see this, and all of a sudden you got a plus here. But then I say, well, there's an H there, and why is that a plus? It's not a plus. There's an H there. Now, how do you get the final product over there? Water adds the cation. What does that give us? We now have oxygen bonded. But that's now a plus charge. How do we get final product?
Water takes one.
Something's got to take it. There's a minus here, sulfate minus or something, or you can use water. Water takes it, leaves us behind, you get that plus what? H3O plus reformed. Okay, when you make alcohol, you have to remove the proton. That's a separate step. How many intermediates in this whole reaction on the board to give the major product? How many intermediates? 3. If you did a reaction coordinate diagram, how many intermediates would you put on it? 3. If you did a reaction coordinate diagram, which intermediate would you put higher? First one or the second? Secondary. Why did you rearrange? Rearrange to a more stable tertiary. So you go to a high, then it would go a little bit lower. Where would you put this at relative to this? This would be even lower. Because this has all octets. And then from there, you would then go down to the very bottom, and you lose the proton. Which step is the rate determining step? It's the same as before. All these reactions forming your carbocation is your rate determining step.
So would you usually do a mental shift if it's if there's 4 carbon bonded to the carbon, then will you be able to shift? So we only use mental shift when it's like quaternary substitution.
Oh, you can do it anytime. Go to a more stable cation.
Is there a limit where that stops being like physically used, like a normal shift or something?
Like a what?
Like something that's a huge chain that's gonna
It can be longer. Can be longer. In general, if it's methyl alkyl propyl, what do you call methyl alkyl propyl? Alkyl. That was an example of an alkyl shift. Okay? You either have hydride shifts or alkyl shifts. Let's look at this next reaction. You take this alkene with a 4-membered ring, react with HBr. Major product has a 5-membered ring. One below, but a 7-membered ring, you react it, look like you're hydrating the alkene. Instead of simple hydration, you actually get this rearranged product. 7-member ring going to 6. Show the mechanism for those two. These are nothing more than just alkyl shifts. Carbocation rearrangements. That's all these are. Except there's a ring there. Okay? Let's pretend we're a ring here, and it's me, you, this guy, and that. There's a 4-membered ring. Okay? See the 4-membered ring? Boom, 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 and boom. Cation over there. And these electrons like it. Now when you happen to be bonded to her also. But then this is the ring. Now, when I rearrange and these electrons break free and move over there, now what size ring do we have? See? All it is just you're doing the same thing, you just got a ring that happens to be there, and the ring, okay. Now, what if I'm here and the cation is there, and I have a 5 and I move this way? I went from a 5 to a 4. Okay? These are just alkyl shifts, but you just have to envision it. And envisioning it is part of just becoming a savvy organic student. Okay? And really understanding. Do these two on your own. We'll look at these first thing next time. You might also show the non-rearranged product. That is, if it just reacted to the alkene. For practice, just show the plain addition reaction. Question?
The sheet that someone has to get that yellow one, would you be able to get tomorrow?
Yes, I'll. So you can stop by. I may have it before then. Because it includes water. Water can act as a neutral solvent. And it can compete with water. That was aqueous, we have water and it. And then whenever water can compete. Because water can act. Understand why we want to dry? We don't want any water there.
But it still needs to be or not dissolved.
But the ethanol could dissolve the HF. HF can be dry. Sulfur can. Dry HF is possible. That's all good. That's all good. Hey.
I'm a desk in my office. I'll share. I'll share. How about one of the ones right here?
Yeah, this is, we got Today is day 8. And they haven't passed on day 8. Day 8 out of 23. Do the math.
People learn that on physics these days, so I don't take it.
That's an interesting way to.
I'm with him. Can we be accepted?
No, Pat, you want we can do a take-home test or a group test. Do you want that?
Why do I feel like no?
I promise you no is the answer.